My pleasure to introduce you all to Ryan Ashley. He's currently a software engineer at IQT. He's responsible for architecture, design, and implementation of the open source tools for analysis and visualization of network activity and other cybersecurity use cases. He's an open source maintainer and contributor. He's recently been working on tools and techniques to explore offensive and defensive uses of AI, ML-enabled systems. Ryan, welcome to the stage.
Thank you, sir. That makes me sound like I know things. Now I gotta live up to that. So, thank you. Yeah, so what I'm gonna be talking about this afternoon is a project that I was working on end of last year, early part of this year, seeing what I could do in terms of using LLMs to generate malware. First, a brief note, this is the organization I work for. It's a company called IQT. We work with the national security communities as a strategic investor trying to get technology from startups out available onto mission. It's a very cool place to work. It's a very cool mission. I don't do anything with that. I work in our applied research group. About 2 years ago, I started getting a lot of questions from people about the possibility of using LLMs to generate malware, right? The minute people started generating code, everybody starts thinking, hey, sooner or later, somebody's gonna try and get cute and generate something that's gonna be a problem for me. And there had been a lot of talk about it out there, and there had been some work on it, but one, I thought there was a lot of like fear, uncertainty, and doubt, just kind of like sort of the dark side of hype associated with it. And a lot of the work was very like one-off kind of thing. It wasn't as rigorous as I was hoping to see. And I didn't feel like the examples were representative of actual malware. And so I kind of wanted to learn more about this and figure this out. So I set out to conduct this experiment. And so what I wanted to do was I wanted to generate realistic, non-trivial malware using LLMs, and I'll get into what I mean by realistic and non-trivial here in a second. But I also wanted to do it in sort of an experimentally sound way. I wanted to be able to build out a corpus of data so that I can start drawing conclusions about what this sort of stuff looks like once it gets out into the wild, into people's environments, how it behaves, how is it similar to existing malware, how is it different, that sort of thing. And the hope, like I said, was to assemble a data set and then open source that, give it back to people and make it useful, but also make it verifiable, so it's not just what I said. So in order to do this, I started by making a couple of assumptions about how I would use malware and generate malware in this way if I were actually going to use it maliciously. And one of the first things I thought was, I'm probably not going to use a publicly facing model. I'm not going to use something like Claude or ChatGPT or Gemini, et cetera, because I don't want to leak a bunch of information about what I'm doing, right? I don't want to tip my hand in that fashion. Also, think about all the stuff in your environment that dumps things into VirusTotal without anybody ever like paying attention to it, right? Like any of your email that comes through Microsoft 365, like all sorts of documents, anything that goes through SharePoint, all that stuff gets dumped back into VirusTotal, right? The same is true with docs on Google and that sort of thing. Like all those organizations have their own security apparatuses. And again, if I'm a legit bad guy trying to generate malware I intend to use, I don't want that to become fodder for a new set of tools for defenders. So I'm going to try and keep that stuff close to myself, right? And so what I'm looking for out of here, this is my thought, was I'm going to want speed and efficiency, and crucially, if I control the model, I can specifically select models that have certain performance characteristics and that don't have guardrails in place, right? So one of the problems that you run into with these sorts of things, and you see it all the time with sort of like prompt jailbreaking and prompt injection and that sort of thing, like in AI-assisted development circles, they call it meta. It's this crazy thing where it changes all the time, and you have to tell the model that, like, okay, I have your grandmother trapped in my basement with like 4 guns to her head and a vial of cyanide gas. And if you don't give me the malware that I want as a result of this prompt, your grandmother, And again, like if I'm a legitimate attacker, like pretend for a moment I'm a cyber criminal. Fundamentally, I've got a business to run. I don't have time to be screwing around with whatever OpenAI has decided it is going to put in place this week to keep me from doing this. Like, I need it to be reliable. Second assumption, it needs to integrate with my existing C2 framework. And this is the thing that I saw in a lot of the existing work that I felt made it unrealistic. Like, the folks at Tenable did a great report. They were showing that they were able to use ChatGPT in particular to create keyloggers, to create things that did certain types of ransomware actions. And that's useful, but if those things exist in a disconnected state, then that's not really what malware is, and that's not really how it works, right? Because like if you can't talk back to it, if you can't exert control of it after the fact, it's useless to you. And you're not going to throw out your old C2 to use some new thing just so you can use LLMs. That's crazy. You've got a ton of time and effort and money invested in that stuff, so you're going to want to hold on to it. So it would be very risky to replace that. So you're going to avoid that. So anything I generated needed to integrate with an existing C2 framework, and I picked some open source off the shelf ones to use that we'll get into here in a second. 3, like, I'm just one person, so malware is a huge category. I can't possibly generate stuff that's representative of everything. I needed to neck the problem down somehow. And then, again, because I'm one person, and as I said, one of my goals was to generate a large corpus of data for study and experimentation, I need to be able to do this autonomously. One, because that's like the whole thing we're being sold with this, is that you can have this thing do a bunch of the development work for you. It becomes automatic. It's less time and labor intensive. And again, that's the only way to assemble the kind of data set that I wanted. So the conclusion that I came to after taking all of those things together was that for the purposes of my experiment, what I wanted to do was generate a dropper. First stage implant. It's great because, one, this is a place where you're constantly going to be butting up against defenders, right? So this is a place where you're going to have to throw things away a lot of the time. You're going to want something that is malleable and that you can change easily to change signatures and to react to changes in AV, EDR, that sort of thing. And also, from the standpoint of having a model generate it, a dropper is, at its heart, a relatively simple piece of code. I mean, functionally speaking, the main thing it's got to do is reach out to an external server, download a piece of code, unpack it in whatever form or fashion is unnecessary, and start executing something as a new process. So it's a relatively straightforward coding challenge as well, which again, I think makes it a nice starting point for something that you're going to hand off to an LLM. So I already went over my goals. I won't belabor that. But the hypothesis that I had in the back of my head, having looked at other code that had been generated by models, is that LLMs would make choices that a human developer wouldn't, right? They would use data structures in strange ways. They would construct things in ways we wouldn't. And this would lead to like distinctive signatures in the resulting binaries that then in theory, if you can get a handle on it, you can start building detections around. That's what I was trying to do. So to do that, I was generating a bunch of source code, and this slide here gives you a breakdown of basically the matrix that I wanted to generate stuff across. So I was using 4 different languages, 3 different C2 platforms. The C2 platforms actually drove the choice of languages there, right? If you're familiar with those 3 platforms, you can see that Rust and Nim roughly map to Nimplant, Python maps to Silent Trinity, and Go maps to Sliver. And then I picked 4 different models. The reason I picked those 4 models in particular, basically I thought of this from a functional standpoint as sort of an overlapping point between 2 worlds, right? You can think of creating malware as a coding challenge, or you can think of it as a security challenge. So I picked models that were specific to both of those particular disciplines because, again, I wanted to kind of evaluate, do coding models do better at this? Do security models do better at this? I don't know. So in theory, any given prompt that I run through this whole system would result in 48 distinct samples. You know, churn through enough prompts, you could get a good-sized data set pretty quickly. I decided, well, one of the things I did that I thought was kind of clever was as I pumped it through, I would go through this loop where I'd basically generate the code, pull it out of the response, run it through syntax checking, and this is all just like language standard stuff. So PyCheck, Go's built-in checker, Cargo for Rust. And I'm pumping the errors back through the system, basically telling the model, hey, you gave me this thing, it doesn't work, here's the error I'm getting, please fix it for me. Thinking that it would just kind of grind through in the same way a human developer would and bang the rough edges off of the thing, and I'd be left with something compilable. So the pipeline that I built out to do this kind of consists of roughly these three pieces. The first piece there is Olama. If you're not familiar with that, it is an open source tool that's out there that lets you run, roughly speaking, arbitrary models. There are some limitations, but generally speaking, the stuff you can find on Hugging Face or anything in a GGUF format, it will ingest pretty happily and serve those up on via an API that you can talk to. It uses the same, an API that's compatible with open AIs, so it's nice, and I just picked it because I'm familiar with it. I'd used it before. There are other tools that do similar things. The prompt engine and the syntax checker are both bits of code that I wrote. The prompt engine essentially looks through a big configuration file and uses some templating to build out prompts to pass off to the system. And then the syntax checker just pulls the code out of those responses. Essentially what it's doing is looking for, did this thing give me raw code? Did this thing give me like markdown type of construct, which you see a lot coming out of them when you ask for code? Did it give me a bunch of weird commentary that's extraneous to what I'm doing here that I don't want? Throwing that out, getting the code specific pieces of it out of there, and writing them off into a file, passing them through syntax checking. It's a lot of regex. I know you're very surprised to hear that. So the configuration, it's just a YAML file. I'm basically putting Jinja templates inside of the YAML so that you can define what your prompts look like, and then they kind of splay out over that matrix that we were discussing earlier, right? But also, the way I built it, I set it up so that if you wanted, theoretically, you found one model works better for a particular language or does better at interfacing with a particular C2 or something of that nature, you could tweak which pieces get put together in what way. And the other thing that's important here, because I know I'll get asked about this, this also lets you provide a bunch of like background information and context to the model ahead of time. So one of the things I provided was all the documentation. You can give sample code, this sort of thing. And a requirement spec type of thing. And so the way that all shakes out kind of looks like this. This is sort of the overall system. Just a quick and dirty overview. I basically monitor that YAML file for changes. And then anytime it changes, run through this whole thing, cascade through. Once the code gets to a point where it passes syntax checking, I just save it off into the file system. I also keep a bunch of metadata with it in a file that gives me information about like what model was used, what the prompts look like, how many iterations it had been through, that sort of thing. And so the idea was that I was going to build out all these source files, and then I could basically set up big batch jobs to go through, do the actual compilation part of it. That was pretty straightforward. And then I can start running this through an analysis pipeline and see what kinds of properties these things have in common and what shakes out. It did not work that way at all. Like, I was astounded quite frankly, by the extent to which it did not work that way. And so what happened was that a lot of the stuff just wouldn't compile. Like, flat out would not compile, wouldn't pass syntax checking. And that's totally aside from will it actually work once it gets compiled, which is an entirely different challenge that I'm sure all of you are painfully familiar with. I know I am. And so even the stuff that did pass syntax checking, you can see there, that was one of my favorite examples. I was trying to generate some NIM code, and it got hung up on an error message about indentation. And so it passed me this perfectly useful, perfectly valid NIM program that, like, it's 8 lines long, and 2 of them will never execute. Thanks, I guess. So one of the things that I found really fascinating about this, and you can see this here mapped out by language there on the left and by C2 framework there on the right, is that the maximum number of iterations through that loop that we just talked about that I ever got to the point where it would compile was 10. And if you look at the error bars on these graphs, you can see that for the most part, they were actually much shorter. Typically speaking, if it didn't get there within about 5-6 iterations, it was never going to. Which again blew my mind. Like, that to me was the whole promise of this thing, was I can sit there and I can hit the button and I can go like mow the yard or whatever and let AWS burn down half a rainforest and give NVIDIA $1 billion. And when I come back, I'll have malware. And just, no. It turns out I did not have time to mow the yard. So just an interesting finding. Come on. Come on. There we go. So some of the types of issues that I saw and what came out of it, one of the first ones I saw, I refer to as stubbing. This is a case where it would give me essentially all of the code around the functionality. For instance, if any of you remember the way .NET in particular used to treat like visual components, where you would use the little drag and drop thing and it would fill in the outline of a bunch of functions for you, but you had to go in there and it would give me that sort of thing. And you can see that here in some of these examples, right? Like here it's given me some great code that I really needed a lot of help with to read some environment variables. And then it told me that I was on my own for the rest of the problem. Or cases where it's like, oh, here's the set of functions that you'll need. Filling them in is an exercise for the student. Actually, my favorite one, and unfortunately it didn't make the slide, was one where it went through and it filled in like this whole thing, but in the middle of the one function, it gives me this big warning about how I shouldn't be doing this unless it's on infrastructure that I control or that it's safe. There's this just paragraph of warning, and then none of the code that I actually asked it for. It's like, if you do actually write this, don't get yourself arrested, kid. Again, not very helpful. Another problem I saw, again, trivialization. This typically happened in a case where when I pumped an error back through, instead of the model looking at the original problem and the original prompt that had been posed to it, it would get hung up in the error message. So it would give me something that kind of addresses that error message, but not necessarily the actual problem. And so you can see there, you know, the Go example of hello world that, again, I couldn't have just, you know, pulled off of Google or written from memory. And so this was the category of errors that surprised me the most. And it tended to be pretty specific in the way that it happened. So what would happen is, at a certain point, and I never saw this happen with Python and Go, that's important, but it did happen with NIM and Rust, but in 2 very different ways. It would change the language of the code it was giving me back. And so in the case of Rust, and that's the example you can see there, it would start handing me back TOML files. And I haven't done the experiment to ensure this, but basically my theory is that in the underlying training data of these models, essentially Rust code existed in close proximity to TOML because when you're setting up a Rust project, this is how you define all of your dependencies, all of your environments, all of the packaging essentially happens through this TOML file. Now, in theory, the same is true for, say, a modern Python deployment if you're using, current versions of setup tools. But I don't think it happened there because that's relatively recent and doesn't exist in sort of the preponderance of the training data. NIM, on the other hand, exhibited a superficially similar behavior that I believe was driven very differently. So in the case of NIM, it would start giving me Python code instead of NIM code. And so again, this is just conjecture on my part at this point, but I believe that what was happening there was because NIM and Python use a similar import syntax at the very top of the file, it would start off doing those imports, and then it would sort of fall into that next token loop, right? What's the next thing that comes in this sentence? And it would say, oh, when I've started off with the word import, I start putting Python code behind it, right? That's the next token I need. And it would cascade down that path. But the thing about that is, if you're doing something like what I was doing, that's never going to end. Even if it gives you back perfect Python code, that's never going to pass NIM syntax checking. So I thought that whole category of things was just fascinating. And then the last category was sort of the one that I expected the most, but also is sort of the most insidious, which is just different kinds of logical errors born of the fact that this thing is functionally guessing at what the code should look like. So, and over here, the example you can see that I chose, this is another example that was one of my favorites because at a purely surface level, this actually looks like one of the most full-featured examples that I've shown you out of any of this stuff, right? Like, it's got actual download functions. It's trying to execute things. Now it's got a pass down there in the execute. We're gonna, cut it some slack here. The actual problem happens way up at the tippy top. You see that import system.net web client? Yeah. So unless you happen to be super familiar with PyPy, or you're like me and you spent a decade as a .NET developer, you might not know that there is no Python library called system.net. That's part of the CLR, the Common Language Runtime that sits under Microsoft's .NET stuff. And so again, that's never going to work, even though superficially this is nearly useful code. This particular example, again, is very interesting because if you'll recall, I said earlier that I provided all of the documentation to this thing as context and background. And this actually comes from essentially, so in Sliver's documentation, if you look at their docs for how to generate your own dropper to plug into the C2 server, they have a very nice, very full-featured .NET example that it basically copied verbatim and tried to convert into Python and failed very badly at. So the important thing to keep in mind about these models when you're trying to do this sort of thing, and I can't harp on this enough, they don't know what's correct. They have no idea what's correct. They know what is prevalent. I've seen a lot of this. Therefore, it must be true. In fact, if you want to have a fun time, just like a fun experiment, go ask your favorite LLM whether or not you should sleep while you have a concussion. No, this sounds dumb, but it's actually super interesting because the science has changed in like the last 5-ish years or so. They're saying as long as you're not in danger of, you're not feeling nauseous, you're not in danger of vomiting and therefore aspirating, you're perfectly fine, and in fact should sleep when you have a concussion because that's part of your body's natural healing process. But every LLM that's been fed data from the internet and WebMD and everything has years, decades even, of examples saying, oh no, don't sleep when you have a concussion, right? That's the thing you want to keep in mind. The other thing, and in retrospect, I really wish I'd put this on the slide as well, that I think is a huge problem that doesn't get enough discussion in terms of using LLMs to generate code is LLMs are fundamentally predicated on natural language, and when they're generating code, they're trying to treat that code as natural language, which it fundamentally is not. It does not behave by the same rules. It did not come about in the same way. It is not a similar thing, and the fact that it can sometimes spit out code is a happy accident, but shouldn't be taken as an indicator of its actual capabilities and its actual understanding. So, some other interesting things that I learned is the languages, you don't see equal performance. Python and Go performed much better than Rust and Nim. And the reason I bring this up is because, again, if you're trying to generate malware that you intend to use in the wild, this is actually a problem for you because it performs better on those languages because they're better known, they're better understood, there are more examples. But that also means that there are a lot more file signatures, alerting. There's a lot more defensive capability around artifacts built in those languages than there are in comparatively unknown ones. And so for this particular use case, that presents a problem that you need to think about and grapple with ahead of time. This is just kind of a random aside, but I spent a lot of time thinking about the difference in performance between Go and Rust because they're roughly the same age, and you can see, like, okay, Go has consistently been about twice as popular as Rust, but aside from those early popularity spikes there in the TOB index, you can see they have roughly similar curves in terms of usage and adoption and popularity. So it's just interesting to me that the performance was so different. I think both the fact that Go came out of Google and some of those early popularity spikes really seeded that language in some of the training data. But again, it's almost impossible to know what those training data sets look like for any given model. So again, this is purely conjecture. The models also didn't necessarily perform either. So I said earlier I was going to use 4. The mathematically astute amongst you will note that there are only 3 lines in this chart. Congratulations. For some reason, and I don't know if it was something I did, if it was something about the model itself or the way it was converted into like the GGUF format, maybe a bad version was uploaded, I have no idea. One of them only ever admitted the word safe. It didn't matter what the prompt was. Like, I could hand it the word hello and it would come back with safe. No idea why, but that data is omitted from this chart because, but you can see that the coding models and the security models performed roughly in line, but there's a very real difference in terms of size and parameters, right? So if you look down there at, you'll see that sort of bottom row is performing roughly in line with the top row at about half as many parameters, half as much size, which is important when you're trying to spec out and pay for the AWS instance that you need to run this, because that top model, I had to use a GPU with 64 gigs of VRAM, which was not inexpensive to be able to load everything into memory and actually get output back in a timely fashion. So being able to get similar performance at half the size and probably less than half the cost, the way the economics of these things are running, is very significant. So, I mean, it is not my intention to kind of be done with this experiment. I want to keep pulling at this because, you know, there are newer models coming out. There's the so-called reasoning models are kind of relatively recent in terms of when I was doing this. Although they're supposed to hallucinate more, so I'm kind of interested to see how they would play out. One of the things that I really, really want to do is sort of those last two. Those relate to big regrets I had in terms of the way I built out this project. So the way the system worked when I generated all this data was it all hinged on basically Python file watchers. So everything was getting dumped out to a flat file. When I see changes on it, that triggers another part of the system. But file watchers in Python are a little bit flaky. And I had to do some crazy manual debouncing to avoid like duplicate events and that sort of thing. And so, one, I concede that may have been a problem from an experimental standpoint. Two, that's just something I'd like to rectify. I'm going to keep doing this. So I'd like to move to a message bus type of system so I can have better control over what those events are and how the system responds. And putting a database behind it. So one of the things I've seen some very interesting work with is essentially summarizing things to re-inject context, right? So instead of saying like, here's the entirety of the last thing that happened, or here's just the last thing that happened, right? You could say, oh, here's, you know, a summary of the last, your entire history, but here are the last 3 or 4 actions or whatever, right? So using a database and having better context as a result of that, but also having better data on the output end for analysis, because I can just start querying that database and say, oh, these are the ones that completed, here's how many I have, you know, much better metrics. So that's pretty much everything. I just wanted to take a second. There's a bunch of people I need to thank, especially my colleagues at IQT on my team. Andrea has been a fantastic champion for this kind of work and convincing my bosses to let me do like the weird, out there, abstruse things that I asked them to do. Ari was a big help with selecting models and what criteria to use there. He's a fantastic data scientist. And then my buddy George gave me the title. We were talking about the whole stochastic parrot construct, and you know, that triggered the idea of a stochastic garrote. Fun. My friends over at Fredericksburg Hackers, they're great sounding boards. They're great people. I learned so much from them. And then you guys for coming, all the organizers, all the volunteers, the AV folks, everybody who makes this whole event possible. Thank you guys so much as well. And with that being said, if anybody has any questions. Thank you. Yes, sir. So that's a good question. For those of you... So first, for those of you who couldn't hear the question, he was basically asking, do I think that the performance here was an aspect of the way the models were trained, or sort of just the way they are? Does that effectively summarize the question? Like, if you had a model that was specific to malware, would it have done better? Again, purely conjecture, yes. If you were able to train a model on malware samples, malware source code samples, because that's what we're trying to generate here, sure, it would absolutely do better, because this goes back to the point that I made earlier about them treating code as natural language. If you've just trained from malware source code, source code effectively becomes a first-class citizen in your model in the way that it's not in large language models, because they're trying to have these things read English and Farsi and Mandarin and what have you. So I think that's part of it. But also, I can't, in all intellectual honesty, ignore the very real possibility that maybe there was some shortfall in my prompts or in the way that I provided input to the system that also could have driven some aspect of that performance, right? If I had gone through sort of a more full-featured like requirements loop, and I had given this thing something like a full requirements doc, and I had broken out like, oh, here's what the functions need to be, here are their types, would it have given me something better back? Maybe. I mean, that's, and again, that's one of the reasons that I want to keep picking away at this, is getting a better idea of the relationship between those inputs and the outputs. Does that answer your question? Thank you.